100 years ago, a mathematician who was barred from being paid to teach quietly outthought every famous physicist of her age. Emmy Noether found that the great laws we treat as commandments, energy that can never be destroyed, momentum that must be preserved, are not commandments at all. They are shadows. Shadows cast by something simpler and stranger underneath, called symmetry. And the forces themselves, it turns out, are summoned into being by it. Beneath the rules of the universe lies a deeper rule that writes them. Tonight we follow that thread all the way down. So get cozy, let the day fall away, and stay with me as the floor beneath physics quietly opens up. Part 1. One page that runs everything. There is a single page of mathematics that quietly governs almost everything you have ever touched, tasted, seen, or loved. You could write it on the side of a coffee mug. You could fold it into a paper airplane and throw it across a room. And yet, the symbols crowded onto that one page describe the behavior of every atom in your body, the light from every star you can see, the way your phone wakes when you reach for it in the dark, and the slow turning of galaxies so far away their light left them before there were eyes anywhere to catch it. One page. That is the part nobody quite tells you when you are young. The universe, for all its size and strangeness, runs on a rulebook small enough to memorize. We tend to assume the great mystery of the universe is that it is complicated, that it is too big, too old, too tangled to ever really understand. But the truth is closer to the opposite, and that is the thing worth sitting with tonight. The deepest surprise of modern physics is not that the universe is hard to predict. It is that the universe is shockingly, almost suspiciously, easy to predict, provided you have been handed the right rules. Give a physicist the rule book and a few starting numbers, and they will tell you where a comet will be in 100 years, what colour a hydrogen atom will glow when you heat it, and how much a beam of light will bend as it grazes the edge of the sundae. They will be right, every time, to a precision that would make a watchmaker weep. So the universe is lawful, it obeys rules. And we have found a great many of them, written them down, and learned to use them with a confidence that borders on arrogance. We landed a machine the size of a washing machine on a comet 4 billion kilometers away, after a journey of 10 years, and it arrived almost exactly where the rules said it would. That is what it means to hold the rulebook. Not to guess, not to hope, but to know. And here is where the real mystery begins, because there are two very different kinds of hidden in this story, and tonight we are going to walk through both. The first kind of hidden is simply the rules we have not yet found. There are gaps in the book, missing pages, sentences that trail off. We will get to those. But the second kind of hidden is far stranger, and it is the one that keeps the people who think about this for a living awake at night. It is this: we can read the rulebook fluently. We can pronounce every word, pass every sentence, use every law to staggering effect. And we have absolutely no idea who wrote it, why it reads the way it does, or whether it could ever have read any differently. Think about how odd that is. Imagine finding a book in a language you can read perfectly, a language that comes to you as naturally as breathing, and realizing you have never met another soul who speaks it. You do not know where the book came from, and you cannot say why it was written in this grammar rather than some other. You would use the book, of course, it works, but somewhere underneath the using, a quieter question would sit and wait. Who decided it should say this? That quiet question is the one we are going to follow all the way down tonight, as far as anyone has managed to go. I want to tell you where we are going so you can settle in for the route. We are going to start with the most beautiful idea in all of physics, an idea most people have never heard of, even though it sits beneath everything else. It has to do with symmetry, and with a mathematician who was kept out of the rooms where physics was decided and then quietly outthought everyone in them. From there, we will go looking for the numbers at the bottom of reality, the fixed settings the rules run on, and we will meet the single most famous and most maddening number in science. A number a brilliant physicist begged his students to pin to their walls and worry about. Then we will do something almost reckless. We will reach into the rulebook and start turning the dials, just to see what a universe with different rules would look like. The answer, it turns out, is usually a universe with nothing in it at all. And finally, we will ask the hardest question of the night. Not which rules, but why there are rules to begin with, and whether we are reading the universe's source code or simply seeing our own reflection staring back out of the page. You do not need to follow every detail. This is not a lecture, and there will be no test in the morning. You only need to let the ideas wash over you, the way the tide comes in, one slow wave at a time. The drama in this story does not come from anything sudden. It comes from the slow accumulation of small facts until, somewhere along the way, the floor of what you thought was solid gives a quiet little lurch, and the universe turns out to be running on rules far stranger than your intuition ever suspected. Because here is the thing about that one page of mathematics. The same rules that make your phone work also fix the color of a star you will never visit, burning in a galaxy whose name we have not bothered to give it. The same law that pulls a dropped cup toward the kitchen floor holds the moon in its orbit and bends the path of light around a black hole. There are no exceptions, not one. In every direction we have ever looked, across distances and stretches of time so large the words for them stop meaning anything, the rules are the same rules. The universe does not keep one set of laws for here and another for there, one for now and another for the beginning of time. It keeps one book and it follows it everywhere, without fail, without complaint, and without ever once explaining itself. So that is the question for tonight, the one we will circle the whole sky to come back to. Who or what decided the rules should be these rules? And the first clue, the very first thread we can pull, is not a law at all. It is something underneath the laws, something simpler and stranger than any single rule, a principle so quiet most people walk right past it. To find it, we have to start not with a force or a particle, but with the idea of sameness itself. Stay with me, because the rule beneath all the other rules is about to come into view. Is less than break time equals 1s. Is greater than number part 2. The rule beneath the rules. In the year 1918, in the German university town of Göttingen, a mathematician named Emmy Noether proved a theorem so beautiful that the physicist Albert Einstein wrote to a colleague calling her work penetrating and important. What makes the story sting is that, at the time, Noether was not even allowed to hold a paid teaching post. She was a woman in a system that had decided women did not belong at the front of a lecture hall, and for years she lectured under a male colleague's name just to be permitted in the room. And in that room, kept at the edge of the very physics she was reshaping, she worked out something that the men with the titles and the salaries had completely missed. She found the rule beneath the rules. To understand what she found, we have to talk about a word you have heard 1,000 times but probably never examined: symmetry. When most of us hear that word, we think of faces and snowflakes and butterflies, of things that look the same on the left as on the right. And that is symmetry, but it is only the smallest corner of it. The real meaning is wider and quieter. Something has symmetry if you can do something to it and have it look the same afterward as it did before. Turn a perfect circle by any angle you like, and it is still the same circle. The turning changed nothing you could measure. That sameness under change, that is symmetry in its true sense, and it turns out the universe is soaked in it. Here is what Noether proved, stated as plainly as I can manage. Every continuous symmetry of the laws of nature produces something that can never be created or destroyed, a conserved quantity, a thing the universe guards so jealously that the total amount of it never changes, no matter what happens. Symmetry on one side, an unbreakable conservation law on the other, locked together forever by a single piece of mathematics. And once you see the pairings, you cannot unsee them, because they explain why some of the most famous rules in all of science are true. Take the most famous one of all. Energy is conserved. You have heard it since school. Energy cannot be created or destroyed, only moved around and changed from one form to another. The chemical energy in your dinner becomes the warmth of your body and the motion of your muscles, but the books always balance. Now, why is that true? For centuries, it was simply a fact you memorized, a commandment with no reason behind it. Noether gave it a reason, and the reason is almost too elegant to believe. Energy is conserved because the laws of physics are the same today as they were yesterday, and as they will be tomorrow. The universe does not care what time it is. Run an experiment this evening, or run it in 1,000,000 years, and the rules that govern it are identical. That sameness across time, that symmetry, is what forces energy to be conserved. The constancy of the law, in time, and the conservation of energy are not two facts. They are one fact, seen from two sides. It keeps going, and it gets better. Why is momentum conserved? The rule that keeps a rolling ball rolling and sends a rocket forward as its exhaust shoots backward. Because the laws of physics are the same here as they are anywhere else. Move your laboratory across the room or across the galaxy, and the rules do not change. Space has no special place, no center, no privileged spot where physics works differently. That sameness across space forces momentum to be conserved. And why is angular momentum conserved? The rule that makes a spinning ice skater speed up the instant she pulls her arms in tight against her body. Because the laws of physics do not care which direction you face. There is no preferred direction in the universe. No cosmic up or down written into the rules themselves. Turn to face any way you like, and physics is unmoved. That sameness under rotation forces the conservation of spin. Sit with what this means, because it quietly rearranges everything. The great conservation laws, the ones we treat as iron commandments handed down from somewhere, are not commandments at all. They are consequences. They fall out, automatically and unavoidably, from the simple fact that the universe has no special moment, no special place, and no special direction. The rules are the same everywhere and everywhen, and because they are, certain things can never change. The bedrock laws of physics turn out to be the shadows that symmetry casts. That is what Noether saw from the edge of the room. And then there is a turn in this story so strange that when physicists first understood it, many of them resisted it for years. Because it is one thing to say symmetry explains the conservation laws. It is another thing entirely to say that symmetry creates the forces. But that is exactly what the 20th century discovered. The forces of nature, the very things we think of as the basic furniture of reality, are not inputs at all. They are demanded into existence by symmetry, summoned to keep the books balanced. Let me try to make that less abstract, because it is one of the most counterintuitive truths in all of science. Imagine you insist that a certain symmetry must hold not just for the universe as a whole, but locally, separately, at every single point in space, each point free to do its own thing. When you make that demand and follow the mathematics honestly, you discover that the only way the universe can possibly satisfy you, the only way to keep that local sameness from tearing the equations apart, is for a force field to spring into being and stitch everything together. Demand a particular local symmetry, and electromagnetism appears exactly as strong as it needs to be, with light itself riding along as the messenger. The physicist Chen-Ning Yang put it in 5 unforgettable words. Symmetry, he said, dictates interaction. The forces are the price the universe pays to keep its symmetries. So now the picture has turned almost upside down from where we started. We began thinking of the rules as a list of laws and forces, the basic stuff of reality. And now we find that beneath the laws lies symmetry, and out of symmetry the conservation laws fall like shadows, and out of symmetry the forces themselves are conjured into being. Symmetry is not one rule among many. It is the rule beneath the rules, the grammar the whole rulebook is written in. But the universe has one more trick with symmetry, and it is the one that may explain why our particular world looks the way it does. Picture a pencil balanced perfectly on its sharp point. The situation is completely symmetric. There is no reason for the pencil to fall in any one direction rather than another. Every way is the same. And yet it cannot stay balanced. It must fall. And the instant it falls, it chooses a direction the perfectly symmetric laws never specified. The symmetry was real, and then it broke, and a particular outcome got frozen into place that the rules alone could never have predicted. Physicists call this spontaneous symmetry breaking, and they believe it happened to the entire universe. In the first unimaginably small fraction of a second after the beginning, the universe was hotter and more symmetric than it has ever been since. The forces we now think of as separate may have been a single unified thing. And then, as the cosmos expanded and cooled, like water cooling past the point where it must turn to ice, symmetries began to break, one after another. The Higgs field, which we will return to later tonight, switched on within a trillionth of a second and gave the particles their masses in the process. Each broken symmetry was like the pencil falling, a choice made that the laws did not require, a detail frozen into our universe forever. And that raises a possibility that should send a small chill down your spine. Some of the rules we treat as eternal and fundamental may be nothing of the kind. They may be frozen accidents, the particular way our universe happened to crystallize as it cooled, no more inevitable than the direction a balanced pencil chooses to fall. If that is true, then symmetry writes the grammar of the rulebook, but it does not on its own fill in every word. Because once you have the grammar, you still need the vocabulary. You still need the actual numbers, the strengths, the masses, the precise values that turn an elegant framework into the specific universe we happen to live in. And those numbers are a mystery all their own, a mystery so sharp that one of the greatest physicists who ever lived confessed he could not explain the most important of them, and begged the next generation to keep worrying about it. To meet that number, we have to leave symmetry behind for a while and go looking for the settings at the bottom of reality. Is less than break time equals 1s, is greater than. Number, part 3. The constants of nature. If symmetry is the grammar of the universe's rulebook, then the constants of nature are the vocabulary, the specific values plugged into the equations that decide how strong, how fast, how heavy everything actually is. You have met some of them, even if you never thought of them as the settings of reality. The speed of light, that cosmic speed limit that nothing carrying information can beat. The gravitational constant, which fixes how fiercely every lump of matter pulls on every other. Planck's constant, the tiny number that sets the scale of the quantum world, the graininess at the bottom of things. These are the famous dials on the control panel of existence, and the equations are full of them. But here is something almost nobody is ever told, a distinction that quietly separates the people who really understand this from the people who only think they do. Not all constants are created equal. Some of them are, to put it bluntly, partly our own invention, an artifact of the bookkeeping we use to measure the world. And some of them are real in a far deeper sense, numbers so fundamental that every civilization anywhere in the universe, no matter how alien, would measure them to be exactly the same. Telling these two kinds apart is one of the most clarifying things you can do, so let me walk you through it slowly. Consider the speed of light. We say it is about 300,000 kilometers every second, and that number feels like a hard fact about the universe. But look closer at what is hiding inside it. A kilometer is a length human beings invented. A second is a stretch of time human beings invented. The speed of light is fast only when measured against the particular meter sticks and clocks we happen to build. If we had defined our units differently, the number would be different, even though absolutely nothing about the universe had changed. The speed of light carries our fingerprints all over it, the marks of meters and seconds, of choices made by committees on Earth. It is real, but part of its value is just us, looking at the universe through units of our own design. This leads to one of the great trick questions in physics, the kind that separates a casual fan from someone who has really thought about it. People love to ask, what if the speed of light were twice as fast? What would happen to the universe? And the unsettling answer is that the question, asked that way, barely means anything at all. Because you could double the speed of light, and then simply redefine what you mean by a meter or a second, and absorb the entire change into your bookkeeping, the universe would not notice. It does not know what a meter is. It never agreed to use our units. Asking what happens if you change a number that has units baked into it is a little like asking what happens to a country if you decide a mile is now a different length. You have changed your map, not the territory. So if the dimensioned constants, the ones with units stuck to them, are partly human bookkeeping, then where are the real rules? They are in the pure numbers, the dimensionless constants. These are the values that have no units at all, no meters or seconds or kilograms clinging to them, just a naked number standing on its own. And because they carry no units, they carry no human fingerprints either. A dimensionless constant is the same whether you measure in meters or miles, in seconds or centuries, on Earth or in a galaxy on the far side of everything. These are the numbers the universe actually chose. These are the settings that mean something. Here is a gentle first example to hold in your mind. Compare the mass of a proton to the mass of an electron, two of the basic ingredients of every atom. The proton is heavier, and when you work out exactly how much heavier, you get a number, roughly 1,836. The proton is about 1,836 times more massive than the electron. Now notice what kind of number that is. It is not 1,836 kilograms or pounds or anything. It is just a ratio, a pure number, the same for everyone everywhere. There are no units to redefine, no bookkeeping to hide behind. The universe simply decided that this ratio should be about 1,836 and not 500 and not 10,000. Why that value? The rulebook does not say. It just hands you the number and moves on. There is another pure number worth pausing on, because it may be the single strangest setting in the whole control panel, and it has to do with gravity. We tend to think of gravity as a powerful force, because it holds us to the ground and keeps the planet swinging around the Sunday. But measured properly, against the other forces, gravity is almost unbelievably feeble. Compare the gravitational pull between two protons to the electric push between them, and you get a pure, dimensionless number, the same for everyone everywhere, and that number is staggeringly small. It is roughly 1 divided by a 10, followed by 36 zeros. To say that gravity is a billion times weaker than electromagnetism is to barely scratch how lopsided it is. You can feel this in your own body every time you pick up a paperclip with a small magnet. That little magnet, with its modest field, overpowers the gravitational pull of the entire planet Earth, tugging the paperclip the other way. The whole mass of the world loses a tug-of-war to a toy. Why gravity should be set so absurdly weak compared to everything else is one of the genuine puzzles of physics, a number we will return to before the night is done, because its weakness may be the most unnatural-looking dial of them all. There is one more thing to do with the famous constants before we go looking for the most maddening number of all, and it is one of the most quietly profound results in physics. Take the three big dimensioned constants, the speed of light, the gravitational constant, and Planck's constant, and combine them together in just the right way. Multiply and divide them so all the units cancel and recombine. When you do, something remarkable falls out. You get a length, a specific, fundamental length built from nothing but the universe's own constants, owing nothing to any human meter stick. It is called the Planck length, and it is small beyond any sensible comparison, about 1/millionth of a billionth of a billionth of a billionth of a meter. To get a feel for how small that is, consider this. A single proton, already so tiny that trillions would fit on the head of a pin, is larger compared to the Planck length than our entire solar system is compared to that proton. You have to descend that far, through that many layers of smallness, to reach it. And the Planck length matters enormously, because it marks the place where our rulebook is expected to fail. At that scale, the laws of the very small, quantum mechanics, and the law of the very large, gravity, are forced to meet, and when they do not get along. The equations stop making sense. Infinities creep in. The rulebook we have used so flawlessly for everything from comets to chemistry begins to stutter and tear. Somewhere down at the Planck length, there is a chapter of the universe's book we simply cannot read yet, written in a language we have not learned. The constants themselves are pointing at the edge of our knowledge, marking the spot where the map runs out. So we have a picture now. Symmetry gives the rulebook its grammar, the shape and structure of the laws. The constants give it its settings, the specific values the laws run on. And here is the thing that should keep nagging at you. Nothing in the laws themselves tells us why the settings sit where they do. The equations are perfectly happy with the proton being 1,836 times heavier than the electron, but they would have been just as happy with a different number. The rulebook describes how the universe behaves given these settings, but it is utterly silent on why these settings and not others. The numbers are inputs we measured, not outputs we derived. And of all those numbers, there is one that stands above the rest. One pure, dimensionless constant, so important that it controls whether atoms can even hold themselves together, whether chemistry is possible, whether you can exist. It is a number we have measured to almost unbelievable precision, and a number that not one human being who has ever lived has been able to explain. The most brilliant minds in physics have stared at it for a century and come away beaten. It is time to meet the magic number. Stay close, because this is the one that haunts them. Is less than break time equals 1s is greater than. Number, part 4, 1/137. There is a number in physics so important and so mysterious that one of the most celebrated scientists of the 20th century told his students, only half joking, to write it on a piece of paper, pin it to their wall, and worry about it for the rest of their lives. The number is roughly 1/137. Physicists call it the fine structure constant, and they usually write it with the Greek letter alpha. It does not look like much. 1 divided by about 137. You could find it on a pocket calculator. And yet this single, naked number may be the closest thing we have to a secret password for the universe. What does it actually do? The fine structure constant sets the strength of the electromagnetic force, which is one of the most important forces in your daily life, even if you never think about it. Electromagnetism is what holds the electrons in their orbits around the nucleus of every atom. It is the grip that binds matter together at the scale of chemistry, and the fine structure constant is the dial that controls exactly how strong that grip is. It decides how tightly an electron is held to its atom. It decides the precise sizes of atoms. It decides the exact colors of light that atoms give off when you heat them, the particular shades of orange and blue and green that let astronomers read the composition of a star from 100 light years away. It decides the speed at which chemical reactions run. In a real sense, This one number sets the terms for all of chemistry, and therefore for everything chemistry makes possible, including the staggeringly complicated chemistry that is currently reading these words. Let that sink in, because the stakes are higher than they first appear. If the fine structure constant were a little larger, the electromagnetic grip would tighten, and atoms and their bonds would behave differently enough that the delicate chemistry life depends on might never get going. If it were a little smaller, the grip would loosen, and matter would hold together in different and probably less interesting ways. The entire architecture of complex molecules, the long, looping, intricate chains that store information and build living things, all of it sits on the value of this one pure number landing in a narrow, workable range. Change the number, and you do not just change a detail. You change whether there can be anything as complicated as a chemist to notice the change. Now here is the part that turned this number into a legend. We can measure the fine structure constant with absolutely extraordinary precision. We know its value to better than 1 part in a billion. To get a feeling for what that kind of precision means, imagine measuring the distance from New York to Los Angeles, more than 3,900 kilometers, and getting the answer right to within the width of a few human hairs. That is how finely we have pinned this number down. We can measure it with breathless confidence, and we cannot explain it at all, not even slightly. There is no theory, no equation, no argument from first principles that tells us why the fine structure constant is about 1 over 137 rather than 1 over 100 or 1 over 200 or any other value. The universe simply hands us the number, and we write it down, and we use it perfectly, and we have no idea where it comes from. This is what so tormented the physicist I mentioned, Richard Feynman, one of the sharpest minds the field has ever produced. He called it one of the greatest mysteries of physics. He described it as a magic number that comes to us with no understanding, a number that, in his words, no man can derive. He said that all good theoretical physicists put it up on their wall and worry about it. And Feynman was not a man given to mysticism or hand-waving. He was famous for his demand that things make sense, for refusing to let anyone hide ignorance behind fancy words. When a mind like that looks at a number and says, plainly, that no one understands it, and perhaps no one can, you are standing at one of the true edges of human knowledge. There is a cautionary tale buried in the history of this number, and it is worth telling, because it shows what happens when brilliant people stare too long at a mystery they cannot solve. In the early 20th century, the fine structure constant looked, for a while, like it might be very close to exactly 1 over 136, and then later measurements nudged it toward 1 over 137. A distinguished astronomer named Arthur Eddington became convinced that the number must be a whole number for profound reasons, and he constructed elaborate arguments from pure logic and numerology to prove that it simply had to be 1 over 136. And then, when the measurements changed, 1 over 137, he was wrong. The number is not a tidy whole number at all. It is 1 over roughly 137.036, an untidy value with digits trailing off. Eddington's failure became a gentle joke in physics, a warning about the human hunger to find clean patterns where the universe has not provided any. Our minds desperately want the magic number to mean something, to spell out a message. So far, it has refused to. And this is why the fine structure constant is the perfect emblem for everything we are exploring tonight. It is the hidden rule made absolutely concrete. Here is a number we use with surgical precision every single day, in laboratories and in the design of the technology all around you, a number woven into the most accurate predictions science has ever made. And it is a number we cannot justify, cannot derive, cannot trace to any deeper reason. Perfect use, total mystery, sitting side by side in a single value. We are like people, who have inherited a flawless instrument and learned to play it beautifully, without the faintest idea who built it or why it was tuned to exactly these notes. There is a distinction worth drawing out here, because it sits at the center of the whole puzzle. There is an enormous difference between measuring something and explaining it. Physics is, without exaggeration, the most successful measuring enterprise in human history. We can measure the properties of the universe to a precision that defies imagination. But measuring is not the same as understanding. We can tell you the fine structure constant to 9 decimal places, and not tell you, in any honest way, why it is not some completely different number. The rulebook gives us the value with perfect clarity and offers not one word of explanation. It is as if every page told you exactly what happens, and no page ever told you why. And here is the thought that should follow you into the next part of our journey tonight. The fine structure constant is not alone. It is not some single outlier, one weird number in an otherwise tidy theory. It is the most famous member of a whole crowd of numbers that our finest theory of nature simply cannot predict and must instead be told. There are a couple of dozen of them, give or take, and every one is a blank that we filled in not by deriving it from principles, but by going out, measuring the universe, and copying the answer into the equation by hand. Our best, most precise, most successful theory of reality turns out to be a rulebook riddled with blanks we had to fill from the back of the book. Just how many blanks are there, and what does it say about us, and about the universe, that we filled them in from the answer key? That is exactly where we are headed next. Is less than break time equals 1s is greater than number, part 5, the numbers we must be told. We like to imagine that our best theory of the universe is a kind of machine you switch on and it tells you everything. Feed it the basic principles, turn the crank, and out comes the world, fully explained, every detail predicted from the ground up. The reality is humbler and far more interesting than that, and once you see it clearly, you cannot quite look at physics the same way again. Our finest theory of the building blocks of matter, the theory we call the standard model of particle physics, is the most precisely tested theory in the entire history of science. It has passed experiment after experiment, decade after decade, predicting the outcomes of collisions and measurements to an almost absurd number of decimal places. And it contains, sitting right inside it, around 24 numbers that it cannot predict at all. Let me be honest and careful about that count, because it matters and because I do not want to mislead you. Depending on exactly how you tally them, and whether you include the masses of those ghostly particles called neutrinos and the way they mix together, physicists quote different figures. You will hear 18. You will hear 19. You will hear about 26. The precise number is partly a matter of convention, of how you choose to slice and bundle things. But the headline truth does not depend on the exact count. Our most successful theory of nature has somewhere in the region of 24 free parameters, 24 settings, that the theory itself is completely unable to explain. They are not predicted. They are not derived. They are measured, by us, in laboratories, and then plugged into the equations by hand. What are these numbers, these blanks we had to fill? They are the most basic facts about the particles that make up everything. They are the masses of the fundamental particles, how heavy each kind of quark is, how heavy the electron is, and its heavier cousins. They are the strengths of the forces, how powerful the strong force is compared to the electromagnetic force, including our old friend, the fine structure constant, which is one of these very parameters. They are the mixing angles, strange numbers that describe how certain particles can morph and transform into one another, blending their identities in ways that have no everyday parallel. And they include the mass of the Higgs particle, the one discovered with such fanfare a little over a decade ago. 24 numbers, give or take, each one a fact about reality that the theory needs but cannot supply on its own. Here is the picture I want you to hold, because it captures the strangeness exactly. Imagine a rulebook, beautifully written, internally consistent, capable of predicting almost anything you ask of it. But scattered through its pages are 24 blank spaces, 24 places where the book says, in effect, insert the correct value here. And the way we filled in those blanks was not by reasoning, not by deriving the values from the deeper logic of the book. We filled them in by going out into the world, measuring the universe with exquisite care, and copying the answers in. We did not solve for these numbers. We looked them up in reality and wrote them down. Our finest theory is a magnificent engine with 24 holes in it, and we plugged the holes with measurements rather than understanding. Where do these numbers come from, then, if the theory cannot generate them? One of the most intriguing possibilities takes us right back to the symmetry breaking we talked about earlier. Remember the balanced pencil, forced to fall in some direction the symmetric laws never specified, freezing a particular choice into place. Many physicists suspect that the values of these parameters were set in just that way, in the first instance of the universe, as it cooled and its symmetries broke one by one. The masses of the particles, in particular, come from how strongly each one couples to the Higgs field, the field that switched on in that first trillionth of a second. But the strengths of those couplings are themselves just more numbers the theory cannot explain. So the masses may have been settled, frozen in, as the universe crystallized out of its hot symmetric beginning, the way a cooling crystal locks in a particular orientation that nothing required in advance. If that is right, then these are not eternal truths carved into the foundations of reality. They are frozen accidents, the particular way our universe happened to set. And there is something almost vertiginous about the spread of these numbers, a feature that makes the mystery sharper rather than softer. The masses of the particles do not cluster tidily around some sensible middle value. They sprawl across an enormous range, with the heaviest of the basic particles outweighing the lightest by a factor of hundreds of thousands, and the ghostly neutrinos lighter still by an amount we have not even fully pinned down. Imagine being handed a set of weights for a scale and finding that they ranged from a feather to a freight train, with no pattern, no rhythm, no obvious reason for the gaps between them. A theory that could explain these masses would presumably tell us why they are spaced the way they are, why this particle is exactly so much heavier than that one. Our theory says nothing of the kind. It accepts each mass as a separate, unexplained gift, hands them all to us in a list, and asks no questions. We are left holding 24 numbers that look less like the clean output of a single elegant law and more like the contents of a drawer someone filled over many years and never sorted. And it gets stranger still, because the rulebook is not only full of blanks we had to fill, it is also, demonstrably, incomplete. There are pages missing entirely. Consider one of the most profound puzzles in all of physics, the simple fact that you exist. When the universe was very young, the rules should have produced matter and antimatter in perfectly equal amounts. And matter and antimatter, when they meet, annihilate each other completely, leaving nothing behind but light. By every naive reading of the rules, the early universe should have made equal parts of each. They should have wiped each other out, and the cosmos should be a thin, cold bath of light, with no matter in it whatsoever. No stars, no planets, no people, and yet here we are, made of matter, in a universe that is clearly not empty. Somehow, for every billion particles of antimatter, there were 1,000,000,001 particles of matter, a tiny imbalance that left a small residue of matter standing after all the annihilation was done. That residue is everything you have ever seen. What caused that imbalance? The known rules contain a small amount of the right kind of lopsidedness, a subtle way in which the universe treats matter and antimatter slightly differently. But when you measure it carefully, That known lopsidedness is far too small to explain the imbalance that actually occurred. There must be more to the rule, some additional source of asymmetry that we have not yet found. And this is the point worth holding on to, because it connects directly to the central thread of our whole journey. The very fact that we are here, made of matter, sitting up at night thinking about the universe, is proof that the rulebook we hold in our hands is not the complete rulebook. There are rules we have not found. Pages are missing. We exist because of a law we cannot yet write down. So this is where we have arrived. Our finest theory predicts almost everything except its own ingredients. It is a triumph of description that quietly refuses to explain itself. Symmetry gives us the grammar of the laws. The constants give us the settings. And almost none of those settings can be explained, while at least one crucial rule is missing entirely. We are holding a book of extraordinary power that is, at the same time, full of blanks and missing pages. Which brings us to the most dramatic question we can possibly ask about all of this. We keep saying these numbers could have been different, that the blanks could have been filled in with other values. But what would that actually mean? What would a universe with different rules, different numbers on the dials, really look like? It is a question we can do more than wonder about. We can take the equations, reach in, and turn the dials ourselves, just to see what comes out. And what comes out, again and again, is enough to make you wonder whether our universe is balanced on the edge of a knife. Get comfortable, because we are about to start rewriting the rules, and watching what happens is less than break time equals 1s is greater than number part 6. Turn the dials and the universe dies. We left the last part with a rulebook full of blanks, 24 numbers the universe handed us without explanation. So let us do the thing the equations quietly invite us to do. Let us reach in, take hold of those dials, and turn them, just to see what kind of universe comes out the other side. This is not idle daydreaming. Physicists do exactly this with the mathematics, adjusting the parameters and following the consequences forward, and what they find is one of the most thought-provoking results in all of science. When you turn the dials of our universe, you almost never get a different universe. You get no universe worth the name at all. Start with the strong nuclear force, the force that binds the centers of atoms together, holding protons and neutrons in their tight little clusters against the electric repulsion that would otherwise blow them apart. Now reach in and adjust its strength, just slightly. Make it a couple of % stronger, and the consequences ripple outward catastrophically. Make it a couple of % weaker, and they ripple the other way just as badly. In some of these adjusted universes, the simplest reactions that power stars never proceed the way they do here. In others, the abundance of the basic elements comes out completely wrong, and the orderly ladder of the periodic table, the foundation of all chemistry, would look nothing like the one hanging on classroom walls. A nudge of a % or two, a tiny turn of one dial, and the chemistry that builds everything either never gets started or gets started in a world too barren to matter. The story of carbon makes this almost eerie. Carbon is the element life is built around, the versatile backbone of every living molecule we know. And carbon is forged in the cores of stars through a delicate process that requires 3 helium nuclei to come together in just the right way. For a long time, it was not at all clear how this could happen often enough to fill the universe with carbon. Then the astronomer Fred Hoyle reasoned backward from his own existence. Carbon exists, he argued, and we are made of it. Therefore, there must be some special feature of the carbon nucleus, a precisely tuned energy level, a resonance, that lets the reaction proceed efficiently. He predicted the existence of this finely placed resonance before anyone had measured it, purely on the grounds that without it, he would not be there to wonder. And when physicists went and looked, the resonance was there, sitting almost exactly where it needed to be. The number that sets it could have been a little different, and the universe would have been starved of carbon, and the chain of events that leads to a living thing reading these words would have been broken before it began. Or take a difference so small it sounds like a rounding error. The tiny gap in mass between the neutron and the proton, the two particles that fill the centers of atoms. The neutron is just a hair heavier than the proton by a fraction of a percent. That hair's width of difference turns out to control enormous things. It governs how the early universe distributed its simplest ingredients, how hydrogen survives, and the precise way stars burn through their fuel and shine. Shift that tiny mass gap one way, and free protons might decay, undermining the stable hydrogen that fuels stars and fills the cosmos. Shift it the other way, and the early universe might have cooked all its hydrogen into heavier stuff, leaving no fuel for the long, slow, patient burning that stars need to warm a world long enough for life to get going. A sliver of mass, and the difference between a universe of enduring stars and a universe that gutters out. And then there is the single worst coincidence in all of physics, a number so finely balanced that it makes everything we have discussed so far look comfortable by comparison. It is the cosmological constant, the number that describes the energy hidden in empty space itself, the dark energy that is gently pushing the universe to expand faster and faster. When physicists try to calculate what that energy should be, based on the churning of the quantum vacuum, they get an answer that is too large, not by a little, but by a factor so enormous it almost defies writing down. The naive calculation overshoots the measured value by something like a 1 followed by 120 zeros. And here is the part that should stop you cold. If the cosmological constant were anywhere near that naively expected value, the universe would have torn itself apart so violently and so quickly that not a single galaxy, not a single star, not a single atom of structure could ever have formed. For the universe to hold together long enough to build anything at all, this one number has to be tuned to a precision of better than one part in that staggering one, followed by 120 zeros. It is as if someone balanced a pencil on its point, and it simply stayed there, against all odds, for 13 billion years. Across all these dials, the same unsettling pattern keeps appearing. The universe looks balanced on a knife edge. Turn the strong force, and chemistry collapses. Shift the carbon resonance, and there is no carbon. Nudge the neutron, and the stars go wrong. Breathe on the cosmological constant, and nothing holds together at all. In setting after setting, our universe sits in a narrow window where atoms can form, where stars can shine steadily for billions of years, where complex chemistry becomes possible, where observers can eventually arise to notice any of it. Step outside those windows, and you find universes that are empty, or formless, or over before they began. Now, I want to be honest with you, because honesty is the whole point of taking this seriously, rather than turning it into a fairy tale. The word fine-tuned carries a temptation, and we should resist leaning on it too hard. We have exactly one universe to study. We cannot run the experiment of creating other universes with other dials and confirming they come out dead. Some of these tunings might be less delicate than they first appear, if changing several dials at once could somehow compensate. And calling a universe tuned for life can quietly smuggle in the assumption that life like ours is the only kind worth counting. These are real cautions, and a careful thinker holds them firmly. The knife edge may be sharp, or it may be that we simply do not yet understand the full shape of the blade. But even with every caution in place, the basic fact remains, and it is enormous. The hidden rules of the universe, those 24 unexplained numbers, are not arbitrary trivia. They are the difference between a cosmos with galaxies and stars and chemistry and minds, and a cosmos that is empty, dark, and structureless forever. This is the most dramatic possible form of the question we have been circling all night. Why these rules and not others? Because with almost any other rules, there would be no one here to ask. The blanks in the rulebook are not just numbers. They are the line between a universe with us in it and a universe with nothing in it at all. And once you have stared at that, you cannot help but ask the obvious next question. If the dials really are set so improbably well, then why? What could possibly explain a universe tuned, against such odds, for its own contents to exist? The answers physicists have reached for are as strange as the puzzle itself, and we turn to them now. Is less than break time equals 1s is greater than number, part 7. The answers nobody can prove. Faced with a universe balanced on a knife edge, with 24 dials set improbably well for stars and atoms and observers, physicists have not simply shrugged, they have reached for explanations. And the remarkable thing about these explanations is that every single one of them is, in its own way, as strange as the mystery it is trying to solve. There is no comfortable answer waiting at the bottom of this question, no tidy resolution that lets you close the book and sleep easy. There are only a handful of bold, unsettling ideas, each brilliant, each deeply problematic, and not one of them yet provable. Let me walk you through them gently, because this is where physics shades into something that feels almost like philosophy. The first idea is called the anthropic principle, and it sounds, at first, either profound or like a trick, depending on your mood. Stated carefully, it says this: we should not be surprised to find ourselves in a universe whose rules permit observers, because we could not possibly find ourselves in any other kind. If the dials had been set to lifeless values, there would be no one there to notice the lifelessness. So, in a sense, the very fact that we are here asking the question guarantees that the answer, whatever it is, had to allow for question askers. It is a little like marveling that you happened to be born on a planet with breathable air and liquid water, when of course you could only have been born somewhere that allowed you to be born. The trouble is that this feels less like an explanation and more like a restatement of the puzzle. It tells us our universe must be the kind that permits us, but it does not, on its own, tell us why such a universe exists at all. For the anthropic principle to have real force, it needs company. It needs there to be other universes for it to select among. And that is exactly what the second idea provides. The multiverse. The proposal is that our universe is not the whole of reality, but one region among unimaginably many, each with its own set of frozen-in rules and numbers. The most developed version comes from a theory about the universe's earliest moments, called eternal inflation, which suggests that the rapid expansion that began the universe never fully stopped everywhere. Instead, it keeps going, endlessly spawning new regions, new bubbles, each one cooling into its own universe, with its own particular settings, as its symmetries break in their own particular ways. In this picture, there is not one rulebook, but countless rulebooks, countless universes, with countless different dials, almost all of them dead and empty, a few of them, by sheer chance, tuned for stars and chemistry and life. And of course we find ourselves in one of the rare hospitable ones, because where else could we possibly be? There is a version of this idea that comes from our deepest attempts at a final theory of physics. When physicists explore string theory, our most ambitious candidate for a theory of everything, they find that it does not seem to predict a single, unique set of rules. Instead, it appears to allow a colossal number of possible configurations, each one a different way the universe could be, each with different constants. The number often quoted is 10 raised to the power of 500. That is a 1 followed by 500 zeros, a number so large it makes the count of atoms in the entire observable universe look like nothing at all. If reality really does explore that immense range of possible rulebooks, then somewhere in that unthinkable lottery, universes like ours, tuned for existence, are bound to turn up. We won a lottery, in this view, with more tickets than there are particles in the sky. And then there is a wilder idea still, one I will flag clearly as speculative, because it is far from mainstream, though it is the work of a serious physicist named Lee Smolin. He proposed something he called cosmological natural selection, and it borrows its logic from biology. Suppose, he said, that universes can give birth to other universes, perhaps through the formation of black holes, each new universe inheriting rules, slightly tweaked from its parent. Then universes whose rules happen to produce lots of black holes would, over countless generations, come to dominate simply because they leave the most descendants. And here is the twist that makes it so intriguing. The conditions that make a universe good at forming black holes, plenty of matter, long-lived stars that collapse, turn out to overlap substantially with the conditions that make a universe good at forming life. In Smolin's picture, our universe is fine-tuned, not because we selected it by observing, and not because we won a cosmic lottery, but because it is the descendant of a long line of universes evolved, generation by generation, toward rules that build black holes and almost incidentally build us. It is a beautiful idea. It may also be completely wrong. We have no way yet to test it. Which brings us to the hard problem that hangs over every one of these proposals, like a cloud that will not lift: testability. Science earns its authority by making predictions we can check against reality, by sticking its neck out and risking being proven wrong. But if the other universes never touch our own, if they leave no signal we could ever detect, no fingerprint in our sky, then how could we ever confirm they are there? An explanation that can never, even in principle, be tested sits in an uncomfortable place. Is it physics, or has it quietly become metaphysics, wearing the clothes of physics? This is a genuine and serious fight within the field, and it would be wrong of me to pretend it is settled. On one side, stand those who argue the multiverse is the natural and even inevitable consequence of our best theories, and that we should follow the mathematics where it leads. On the other side, stand those who insist that an untestable multiverse is no explanation at all, just a way of dressing up our ignorance in cosmic robes. Both sides are made up of brilliant, careful people. Neither has won. But step back from the particular proposals for a moment and notice what they all have in common, because this is the thread that ties them to everything we have said tonight. The anthropic principle, the multiverse, the string range of possibilities, cosmological natural selection, every one of them is, at bottom, an attempt to answer the same single question: why these rules and not others? They differ only on the deepest possible point. Were the rules selected, picked out from a crowd of alternatives, because only these permit observers? Were they derived, the unique output of some final theory we have not yet finished? Or do they simply are brute facts with no further explanation, the way they are, because that is how reality happens to be? We do not know which of these is true. We may never know. And whichever it turns out to be, it forces us back to an even more basic question, one we have been postponing all night. We have been asking whether the rules could have been different. But there is a prior question, a more nervous one. Before we ask why the rules are what they are, we had better make sure they are even fixed at all. Are the constants really constant? It is time to find out. Is less than break time equals 1s? Is greater than number part 8? Are the constants constant? We have spent this whole journey talking about the constants of nature as if they were exactly that, constant, fixed. The same yesterday and tomorrow, the same here and on the far side of the observable universe. We have treated the fine structure constant and its companions as bedrock, the unchanging settings the universe was switched on with. But that assumption deserves to be questioned, and questioned hard, because it is one of the most natural assumptions to make and one of the most dangerous to make without checking. Before we keep asking why the rules are what they are, we should make absolutely sure of something simpler. Are the rules even the same everywhere? Or could the constants themselves be drifting, varying across the sky or across the ages in ways we have mistaken for permanence? How could you possibly test such a thing? You cannot travel to a distant galaxy and set up a laboratory. But the universe has handed us a trick that is almost like time travel, and it is one of the most elegant tools in all of astronomy. When light from an extremely distant object, billions of light years away, travels toward us, it has been traveling for billions of years. We are not seeing that object as it is now. We are seeing it as it was when the light left, billions of years ago. The light is a fossil, carrying a record of the distant past frozen into it. And here is the beautiful part. When that ancient light passes through clouds of gas on its long journey to us, the atoms in those clouds absorb very specific colors, leaving dark lines in the spectrum, a kind of barcode. And the exact spacing of that barcode depends, sensitively, on the value of the fine structure constant at the time and place the light passed through. So by reading the barcodes in ancient light from across the universe, we can, in effect, measure what the fine structure constant was doing billions of years ago and billions of light years away. When astronomers did this, using light from distant, brilliant beacons called quasars, some of them found something that set off a quiet earthquake in the field. Looking at a large collection of these ancient measurements, around 150 of them gathered from telescopes in both hemispheres, a pattern seemed to emerge. The fine structure constant did not look perfectly uniform across the sky. Instead, it appeared to be very slightly larger when they looked in one particular direction, and very slightly smaller when they looked in the opposite direction. A lopsidedness across the heavens, what they called a dipole, pointing toward a particular spot in the sky, and reported at a statistical significance that hovered around 4 sigma, which in plain terms means it was unlikely, though not impossible, to be pure chance. Sit with how strange that claim is, because if it were true, it would be one of the most important discoveries in the history of science. It would mean that the strength of electromagnetism, the grip of that magic number we worried over earlier, is not the same throughout the universe. It would mean that if you travelled far enough in one direction, atoms would bind a touch differently, chemistry would run on slightly altered terms, the rulebook itself would read a little differently than it does here. The constants would not be constants at all. They would be more like a slowly changing weather, varying gently from one cosmic region to another. The very bedrock would turn out to be tilted. But, and this is a large but, the claim is fiercely contested, and a careful mind has to hold the doubt as firmly as the wonder. Many other measurements, made by other teams looking at other systems, have found no variation at all, results perfectly consistent with the constants being rock steady, and the skeptics raise a pointed concern. Measuring these tiny barcode shifts demands almost impossibly precise calibration of the instruments, and subtle errors in how a spectrograph maps colors could mimic exactly the kind of signal that was reported, producing the illusion of a varying constant where there is none. The dipole, in other words, might be real new physics, or it might be a ghost born from the imperfections of our machines. As things stand, it is not confirmed. It is a tantalizing, unresolved hint, the kind of thing that keeps a field honest and awake, neither proven nor put to rest. So astronomers and physicists have brought the question home into the laboratory where they can control everything. Around the world, scientists are building networks of the most precise clocks ever made, atomic clocks, and even more exotic clocks based on single molecules and highly charged ions, accurate enough to lose less than a second over the entire age of the universe. By comparing different kinds of these clocks against one another over months and years, they can hunt for the faintest drift in the fundamental constants happening right now, in real time, here on Earth. They are even searching for a wilder possibility that the constants might oscillate, gently wobbling back and forth, if they are secretly coupled to the dark matter that fills our galaxy. And so far, the laboratory verdict is clear and a little reassuring. Within the limits of these extraordinary instruments, the constants are holding perfectly still. No drift, no wobble, no change. The bedrock, at least here and now, appears to be exactly as solid as we hoped. The universe has even left us a natural experiment on this very question buried in the ground in West Africa. Roughly 2 billion years ago, in a place we now call Oklo, a deposit of uranium ore became so concentrated, with groundwater seeping through it just so, that it spontaneously began to sustain a slow nuclear chain reaction, an entirely natural reactor that ran on and off for hundreds of thousands of years before going quiet. When scientists studied the leftover products of those ancient reactions, they realized they were looking at a frozen record of nuclear physics as it operated 2 billion years in the past. And the way those reactions proceeded depends, sensitively, on the value of the fine structure constant back then. So Oklo became an accidental laboratory for measuring whether the magic number has drifted over 2 billion years of Earth's own history. The verdict from that buried reactor is that the fine structure constant has changed by, at most, a vanishingly tiny amount over 2 billion years, and quite possibly not at all. Here on our own world, reaching back a good fraction of the age of the universe, the rules appear to have held perfectly still. And this is why the question matters so much for everything we have been exploring. Whether the constants hold steady across all of space and all of time is not a technical footnote. It is a direct measurement of how fundamental the hidden rulebook really is. If the constants are truly fixed everywhere and everywhen, then they are bedrock in the deepest sense, the unchanging foundation of reality. But if they drift, if they vary from place to place or age to age, then they are not bedrock at all. They are more like the local weather of physics, conditions that happen to hold here, blown into place by some deeper process we have not yet identified. The rules we thought were eternal might be merely current. We do not yet have the final answer. The hint in the ancient light still flickers, unconfirmed. But there is one more way to test the rulebook, and it does not look across the sky at all. It looks downward, into precision so extreme that the slightest crack in the rules would have to show itself. And for a few years, it looked like a crack had finally appeared. Is less than break time equals 1s is greater than number part 9. The muon that almost broke the rules. There are two ways to test a rulebook. You can read it in faraway places, as we just did with the ancient light from quasars, checking whether the rules hold across the sky. Or you can stay right here and read a single sentence of the book so closely, with such fanatical precision, that if there were even the tiniest error in it, the smallest crack in the rules, you would catch it. For the last several years, one of the most dramatic stories in all of physics has been exactly this second kind of test, and it's centered on one of nature's stranger little particles, a thing called the muon. The muon is, in the simplest terms, a heavy cousin of the electron. It carries the same electric charge as the electron, but it is about 200 times more massive, and it is unstable, flickering out of existence in a tiny fraction of a second after it is made. Like the electron, the muon behaves in some ways like a tiny spinning magnet, and the strength of that little magnet is described by a number physicists call its G factor. And our rulebook, the standard model, predicts the value of that G factor with ferocious, almost obsessive precision. This makes the muon a nearly perfect place to test the rules, and the reason why is genuinely beautiful. Here is the subtle thing. The muon's magnetic strength is not set in isolation. According to the rules, that little magnet is constantly being nudged and tweaked by every other kind of particle in existence, including particles that are not really there in the ordinary sense, particles that flicker in and out of the empty space immediately around the muon, borrowed briefly from the vacuum, and then repaid. Every type of particle that exists contributes its own tiny tug to the muon's wobble, which means that, if there were some particle we have not yet discovered, some missing piece of the rulebook, it too would leave its fingerprint on the muon's magnetism, shifting it by a minuscule amount away from what the known rules predict. So by measuring the muon's wobble with enough precision and comparing it to the prediction, you are essentially asking the universe whether our list of particles is complete. A mismatch would be a signpost pointing directly at undiscovered physics. And for years, there seemed to be a mismatch. At a laboratory in the United States, physicists measured the muon's wobble over and over, with steadily improving precision, and the answer they got sat stubbornly away from the standard prediction, off by an amount that grew, as the measurements sharpened, to around 5 sigma. In the language of physics, 5 sigma is the gold standard for a discovery, the level of statistical confidence at which you are allowed to say you have found something real. The muon appeared to be wobbling just a little more than the known rules said it should, and the whole field held its breath, because the most exciting explanation was that the extra wobble was the fingerprint of some new particle, some unknown force, a genuine crack in the rulebook, through which we might finally see beyond the standard model into the deeper physics everyone suspects is waiting. For a while, it was the most tantalizing hint in particle physics, a door that seemed to be creaking open. Then came the resolution, and like many things in real science, it was quieter and more complicated than the dream. The final measurement, announced in the middle of 2025, reached a precision of 127 parts per billion, the most exquisite measurement of the muon's magnetism ever achieved. To get a feeling for that precision, imagine weighing a fully loaded jumbo jet and being certain of the answer down to the weight of a single grain of rice. That is how finely the muon's wobble was pinned down. But the crack in the rules did not survive, and the reason is fascinating. The problem was never really with the measurement. The problem was with our ability to calculate what the rules actually predict. One part of the prediction, involving the messy, hard-to-compute effects of the strong force, had been worked out 2 different ways, and the 2 methods disagreed. As physicists refined the more fundamental calculation, the kind done by simulating the equations directly on enormous supercomputers, the predicted value shifted upward, moving to meet the measurement. And when the dust settled, the gap had shrunk from a thrilling 5 sigma down to around 1 sigma, which is no real disagreement at all. The anomaly faded, the standard model held. The door that seemed to be opening turned out, on closer inspection, to be closed after all. If you want to feel just how good our rulebook really is, set the muon aside for a moment and look at its lighter sibling, the ordinary electron, which has a magnetic wobble of its own. The electron's wobble is the single most precisely tested prediction in the history of science. When you measure it and compare it to what the rules predict, the measurement and the theory agree to about 12 decimal places. 12. To picture what that kind of agreement means, imagine measuring the distance across the entire United States and having your prediction come out right to within the thickness of a single human hair. And then imagine being 100 times more accurate than that. That is the level at which the electron obeys the rulebook. A theory that nobody can fully explain, built on numbers we simply had to measure, predicts the behavior of an electron correctly to 12 decimal places. There is nothing else in human knowledge that works this well. We have, in our hands, the most accurate description of anything that our species has ever produced, and we cannot say where its deepest rules come from. I will be honest with you about the feeling among physicists when this happened, because it is more human than you might expect. There was relief, of course, at finally understanding the situation, and admiration for the sheer precision of the work. But there was also a small, genuine heartbreak, because many physicists had quietly hoped the crack was real. A crack in the rulebook is not a failure. It is a door. It is the way forward, the way you discover the next layer of reality, the missing pages everyone believes are out there somewhere. To watch a promising crack seal itself shut, to see the old rulebook vindicated once again, is to be sent back to the drawing board, still locked out of the deeper physics we are all certain must exist. The muon had teased us with a brief sighting of what lies beyond, and then taken it away, and there is a quieter lesson hiding in this whole saga, one that connects straight back to everything we have been saying. Notice that the difficulty was not in measuring the universe. We measured the muon's wobble to a precision that beggars belief. The difficulty was in knowing what our own rulebook even predicts. Two camps of brilliant physicists disagreed for years, not about the universe, but about what the equations they both accepted actually say. The rulebook is so subtle that reading a single sentence of it correctly took decades of argument and the world's largest computers. So here is where the muon leaves us, and it is a strange place to be. Every time we test the hidden rules to the very edge of precision, every time we go looking for the crack that would let us see beyond them, the rules survive. They pass the test. They hold. Our rulebook is almost suspiciously good, performing flawlessly even at the 11th decimal place, even under the most punishing scrutiny we can devise. And that only sharpens the central mystery of the night. How can a set of rules that nobody can explain, rules full of unexplained numbers and missing pages, be so relentlessly, perfectly correct? Which forces us, at last, to stop asking which rules the universe follows, and to ask the strangest question of all. Why is there a rulebook at all? Is less than, break time equals 1s, is greater than? Number, Part 10. Why is there a rulebook at all? We have spent the whole night asking which rules the universe follows and why the dials are set where they are. But there is a question lurking beneath all of that. A question so basic it is easy to walk right past, and it is the one we turn to now. Forget, for a moment, why the rules are these particular rules. Ask instead why there should be rules at all. Why is the universe lawful? Why is it the kind of place that can be captured in equations, predicted, understood? It did not have to be this way. We can imagine a reality that is simply chaotic, lawless, different from one moment to the next, a place where nothing could ever be predicted because nothing ever repeated. Instead, we got a universe so orderly that a few symbols on a page can forecast the behavior of a star. Why? The physicist Eugene Wigner gave this puzzle a name that has stuck for more than 60 years. He called it the unreasonable effectiveness of mathematics. Here is what he was pointing at. Mathematics is, in large part, something human beings invent for their own reasons, exploring abstract patterns and structures purely because they are interesting, with no thought of the physical world at all. And then, again and again, across the history of science, some piece of that abstract, invented mathematics turns out to describe reality with uncanny precision, as if it had been waiting all along for the universe to need it. A branch of pure geometry, dreamed up to amuse mathematicians, becomes the exact language of curved space-time. Strange abstract structures become the precise grammar of particle physics. Why should the free inventions of the human mind fit the cosmos like a key fits a lock? Wigner called it a wonderful gift which we neither understand nor deserve. The effectiveness of mathematics is not something we have explained, it is something we have simply gotten used to. The mystery has a sharper, more technical edge too, and physicists run into it constantly. There is a principle they call naturalness, the expectation that the numbers in a fundamental theory should not be wildly, delicately balanced for no reason. And our universe seems to violate it. The mass of the Higgs particle and the astonishing weakness of gravity compared to the other forces look unnaturally fine-tuned, as if a dozen huge quantities had to cancel out to many decimal places by sheer coincidence to leave the small values we observe. For decades, physicists had a favored solution to this discomfort, a beautiful idea called supersymmetry. which proposed a whole hidden family of undiscovered partner particles that would naturally cancel the troublesome quantities and restore order. It was elegant. It was widely expected. And when the largest machine ever built, the Great Collider near Geneva, went looking for those partner particles, it found nothing, no superpartners. The most natural solution to the naturalness problem simply did not show up. And that absence has pushed some physicists toward an uncomfortable conclusion, the suspicion that the universe simply is not natural in the way we hoped, which loops us right back to the ideas from earlier tonight, the multiverse and the anthropic selection of strange, finely balanced rules. The failure to find naturalness is itself a clue, nudging us toward the possibility that our rulebook was selected rather than derived. And then there are ideas at the very frontier, the ones I will flag clearly as speculative, where physics begins to shade into something stranger. The physicist John Wheeler, near the end of a long and visionary life, became convinced that the deepest layer of reality might not be particles or forces or fields at all, but information. He coined a phrase for it, it from bit, the notion that every physical thing, every it, derives its existence from answers to yes or no questions, from bits. In this view, the rulebook is written, at bottom, not in matter, but in information, and the physical world bubbles up from something more like computation than like substance. This idea has grown into a serious thread in modern physics, feeding into the study of black holes and the strange suggestion that our three-dimensional reality might be encoded, like a hologram, on a distant, two-dimensional surface. The rules, in this telling, might be the rules of information itself. Push a little further out, and you reach the wildest shores, ideas I offer purely for texture, not for belief, because they cannot be tested and may never be. There is the proposal, made seriously by some thinkers, that reality does not merely follow mathematics, but is mathematics, that the universe is a mathematical structure, existing in the same way a perfect circle exists, and we are self-aware patterns within it. And there is the idea, popular in late-night conversations and serious enough that a few physicists have entertained it, that a universe running on fixed rules with a smallest possible scale, a kind of resolution limit down at the Planck length, looks suspiciously like a computed reality, a simulation. I do not raise these because I think they are true. I raise them because they show how far the question stretches, how the simple wonder of a lawful universe can carry you all the way to the edge of what can be thought, let alone known. So let us lay out the live possibilities calmly, the way you might lay out 3 roads at a crossing in the dark. The first possibility is that the rules are fundamental, that there exists, waiting to be found, a final theory, a deepest layer, from which all the symmetries and all the numbers can be derived with no blanks left over, and that one day we will read the rulebook all the way to its first page. The second possibility is that the rules are emergent, that they are not fundamental at all, but bubble up from something deeper, from information, or from the structure of space-time itself, the way the smooth flow of water emerges from the chaotic dance of molecules that know nothing of flowing. And the third possibility, the most vertiginous of all, is that the rules are, in part, a reflection of the minds that read them, that the order we find is partly the order we are built to find, and that a different kind of mind might carve the universe at different joints entirely. We do not know which road is the true one. We may be standing at this crossing for a very long time. But notice, as we close in on the end of our journey, that every one of these roads is an answer to the very question we started with all those hours ago when we held up that single page of mathematics and marveled that it runs everything. Who wrote the rulebook, and in what language? Is it written in fundamental law, in emergent information, or partly in the structure of our own understanding? And there is one last thread to pull before we rest, a small, loose end with an enormous question tied to it. If the rulebook really is written in mathematics, and mathematics, at least in part, lives inside our heads, then where exactly is the rulebook? Out there, in the universe, waiting to be discovered? Or in here, in the mind, projected onto a cosmos that never agreed to any of it? Hold that question gently as we come, at last, to the end. Is less than break time equals 1s? Is greater than number, part 11. Reading the source code. Let us gather everything we have found tonight and hold it all at once, the way you might hold a single, complicated thought just before sleep. We began with a page of mathematics small enough to fit on a mug, a rulebook that governs every atom and every star, and we set out to understand it. We found that beneath the rules lies symmetry, the quiet grammar of the universe, and that from symmetry the great conservation laws fall like shadows, and even the forces themselves are summoned into being. We found that the rules run on settings, on constants, and that the truest of these are pure numbers the universe simply handed us, like the magic number near 1/137 that no one can explain. We found that our finest theory contains around 24 such numbers it cannot derive, blanks we filled in by measuring reality and copying the answers by hand. We reached in and turned the dials and watched universe after universe die, and we saw how narrow the window is that allowed anything at all to exist. We chased the proposed explanations, the anthropic principle, and the multiverse, and the rest, and found them as strange as the puzzle. We tested whether the rules even hold, across the sky and down to the 11th decimal place, and watched them survive every challenge. And we asked, finally, why there should be a rulebook at all, and found 3 roads into the dark, none of them yet taken to its end. And here is what it all comes down to. The single fact that has been sitting at the center of this whole night like a stone at the bottom of a clear pool. We hold a rulebook of extraordinary power. We use it with surgical precision. We trust it enough to send machines across the solar system and to build the technology that fills your home. And we cannot say where it came from, why it reads the way it does, or whether it could have read differently. Perfect use, no understanding. That is the strange and humbling position of our species. We are fluent readers of a book whose author we have never met, whose language we did not invent and cannot fully account for, and whose first page we have never seen. There is a hopeful way to hold this, and it is true, and I want to offer it to you. Each generation reads a little further into the book than the one before. The blanks of one century have a way of becoming the theorems of the next. Things that seemed like brute, unexplainable facts to our grandparents, the spectrum of an atom, the binding of a nucleus, turned out to have reasons we now teach to students. There is no law that says our current blanks must stay blank forever. Perhaps the 24 unexplained numbers will one day fall out of some deeper theory as naturally as the conservation of energy fell out of symmetry. Perhaps a future mind, reading these very questions, will smile the way we smile at the puzzles of the past and wonder how we ever found them mysterious. But there is a humbling way to hold it too, and honesty requires that we sit with this one as well. It may be that some of the blanks are not meant to be filled by reasoning at all. It may be that when we ask why the fine structure constant is what it is, or why there are these rules and not others, we are asking a question shaped like the question, what lies north of the North Pole? A question that sounds perfectly sensible, that our minds insist must have an answer, but that quietly dissolves when you look at it closely, because there is simply no more north to be had. Perhaps the universe is this way, because it is this way, and why is a door that opens onto nothing? We cannot yet tell the difference between a mystery we have not solved and a mystery that has no solution. Both feel exactly the same from the inside. There is something worth noticing about our own strange position in all of this, something easy to miss because we are too close to it. You are made entirely of things that follow the rules. Every atom in you obeys the fine structure constant without ever being asked. The particles in your fingertips conserve their energy and their momentum because the universe has no special place or moment, exactly as Emmy Noether worked out from the edge of a room 100 years ago. You did not agree to any of this, and you cannot opt out of it. You are, in the most literal sense, a passage of the rulebook that has been written into matter and set in motion. And yet, somehow, this particular passage of the book has folded back on itself and started to read the rest. The rules built a thing that could contemplate the rules. That is a stranger loop than any equation, a part of the universe that turned around to study the laws that made it, using a mind that those very laws assembled. Whatever else the hidden rules are, they are the kind of rules that, given enough time and the right conditions, produce readers. And it is worth being honest that this may be the closest we ever come to an answer, and that this might have to be enough. For most of human history, people looked at the sky and saw the will of gods, or nothing at all, or patterns they invented to comfort themselves in the dark. We are the first creatures who can look at the same sky and read, in the light of distant stars, the actual rules those stars obey, the same rules that govern the candle on your table and the blood in your veins. We may not know why the rules are what they are. We may never know, but we got far enough to ask the question precisely, to measure our own ignorance to many decimal places, to know exactly the shape of what we do not understand. That is not nothing. That is, in fact, an astonishing distance to have travelled for a species that, not so long ago, did not know the earth went around the Sunday. And maybe, just maybe, the deepest hidden rule of all is not any single law or symmetry or number that we have chased tonight. Maybe it is something we have been standing inside the whole time without quite seeing it. The bare, astonishing fact that the universe is lawful at all, that it is knowable. That reality, which had no obligation to make any sense whatsoever, turned out to be ordered enough that a small, warm, temporary arrangement of matter, a few pounds of carbon and water, that the universe assembled out of dead stars, can sit up in the dark and read the rules that made it. The universe wrote a rulebook, and then, after 13 billion years, it grew something inside itself that could open the book and begin to read. That may be the strangest rule of all, and it is the one we tend to forget, because we are it. So whether we are reading the universe's own source code, the genuine first principles written into the foundation of reality, or whether we are seeing our own reflections staring back out of the page, the order of our own minds projected onto a cosmos that never asked for it, the truth is that we cannot yet say which. The reading goes on. The book is still open. And tonight, as you let these questions settle and the day finally falls away, you can rest in this one quiet thought. You are a part of the universe that woke up and started to read. Whatever the hidden rules turn out to be, and wherever they turn out to be written, the reading itself, the simple fact that any of this can be understood at all, may be the most mysterious rule the universe ever followed.